In this section, we will discuss the three states of data, starting with the lesser known data in use, and then covering the well-known data at rest and data in transit states. Data in use is when it is loaded in memory and used by running applications. Attacks on data in use have already happened with the 2014 data breach on Target's credit card processing point-of-sales systems using RAM scraping malware. Data in use is very difficult to protect because of an architectural flaw in the underlying operating system architecture of all popular operating systems today. As a result, all DLP and IRM products leave data in use unprotected and can all be attacked by RAM scraping malware. Contact A1Logic using the contact information at the end of this course for a demo of a universal and unfixable bypass in all data loss prevention and information rights management products in the market today. Hypervisors can be used to protect data when it is in use in memory. With hypervisors, the application can run unmodified and the protection would not have to know about the internals of the application or the data that it consumes or produces if all the data that is written out of the virtual machine is forcibly encrypted. We already talked about the value of hardware foundations in enforcing security. Intel's x86 VTX extensions allow hardware-enforced isolation of the VM's memory away from the untrusted environment. New memory security technology from the hardware vendors, such as Intel and AMD, are allowing encryption of the memory at a VM granularity. As a result, the VM with memory encryption becomes almost equivalent to Intel SGX. One of the biggest strengths of using hypervisors, as already mentioned, is that it does not require modifying applications, which means that it allows both backward and forward compatibility with legacy applications and future applications that have not even been written yet. Since a VM emulates a physical machine and all applications run on physical machines, the general trend is that all applications can run in VMs and therefore can be protected by hypervisors. In addition, tricks can be played with the hypervisor to juggle the user input and output devices in such a way that data traveling to or from the hardware never passes through an untrusted environment. The result of this hardware pass-through is that the user can safely interact with the applications using regular mouse and keyboard input as they would expect, and they can see the output on the screen as they would also expect. This is a bigger deal than it sounds because we will see in the next few slides that SGX currently does not allow safe user input and output. When hypervisor-based security is combined with memory encryption, it takes the memory encryption strength of Intel SGX without the weakness of requiring the application to be modified or allowing the user input or output to travel through untrusted environments. In order to comply with the unchanged user experience concept discussed earlier, multiple windows from multiple VMs can be forwarded and composited onto a single screen simultaneously. This would give the user the same natural experience that they are used to when working with multiple windows side by side from multiple applications running on a single operating system. If multiple graphical windows are running in seamless mode, the user might not even know that there is a security hypervisor running behind the scenes and protecting data. This is the way security software should be, unobtrusive and out of the way. Hypervisor-based security combined with memory encryption is the best of both worlds. The left side shows what happens when data is unprotected in use. Malware can get onto the system using low-hanging fruit, such as a browser exploit, and can steal sensitive information from other programs that are running, such as Acrobat in this case, which might have a PDF file open. The right side shows what security can be achieved when hypervisors are used to isolate and protect sensitive data in use. You can see that the malware is trapped in the untrusted VM and cannot jump across the hypervisor to access the data in use in Acrobat in the trusted VM when a PDF file is open. Intel SGX can be used to protect data in use. SGX loads the code and the data in an encrypted memory enclave and executes the code on the data. One of the biggest problems with Intel SGX is that the SGX enclave acts like an island of trust in the middle of an untrusted environment. User input and output cannot get to or from the SGX enclave island without passing through the untrusted environment, where its confidentiality and integrity can be compromised. There is no public way to solve this issue right now. An exploitation of this vulnerability would be keylogging malware, stealing keyboard input before it gets to the code running in the enclave, and taking screenshots of sensitive data after it leaves the enclave, but before it is displayed on the screen. Another big weakness with SGX is the fact that the application must be modified in order to take advantage of the x86 SGX extensions. This means that all applications that need to be protected would have to be modified and redeployed. This violates the concept of backward compatibility discussed earlier. The blog post linked here gives more in-depth information about SGX versus hypervisors and references academic papers on the subject. In this diagram, applications number 1 and number 3 have no way of protecting data in use. Intel SGX helps application number 2 protect its data in use. This diagram also shows the problem with the SGX enclave being the island of trust that we mentioned earlier in the middle of an untrusted environment. There is no trusted input path from the keyboard or mouse to the enclave, and there is no trusted output path from the enclave to the display. Homomorphic encryption is another way to protect data in use through innovations in cryptography. With homomorphic encryption, operations and computations are done directly on ciphertext. This means that data never has to be decrypted in order to be used, thereby keeping the data protected when in use. Homomorphic cryptography has limitations similar to those of Intel SGX. First of all, if the environment is not trusted enough to decrypt data when it is in use, it is probably not trusted enough to allow sensitive user input and output to pass through it either. As a result, there is no way for a user to securely interact with the application. Also, all the standard applications that we use today expect to process unencrypted data. They would have to be rewritten in order to operate on ciphertext. The requirement to rewrite the applications violates the backward compatibility concept that we discussed earlier. This is a conceptual diagram of homomorphic encryption. If M is the input and there is a function f performed on it and the result is encrypted, the result would be the same as if M was first encrypted and the function was evaluated on the ciphertext of M. Data at rest is when it is stored on a disk, and data at rest is generally well protected today by encryption. There are two main types of data at rest encryption: file encryption and disk encryption. File encryption provides more security because it is more granular and at the file level, which allows the encryption to follow the file wherever it ends up, even if it is exfiltrated. Disk encryption, however, is less granular than file level encryption and therefore provides less security. Disk encryption mostly protects against the device being lost or stolen, rather than the file being uploaded by a legitimately logged on user or malware impersonating a legitimately logged on user. Database column encryption is similar to disk encryption in that the encryption does not follow the data. Storing encrypted data in the database is more granular and allows the encryption to follow the data, even if the cell is read out of the database or uploaded. A system is more secure if encryption is more granular. We must assume that data exfiltration is occurring because files can legitimately be stored outside the enterprise, such as on employees' devices or in clouds. The thing that we cannot verify is whether those employees' devices or those clouds are safe. Data in transit is when it is transferred over a public medium that the attacker has access to. Data in transit is generally well protected by today's security software. Many network protocols exist today to protect data in transit. Today, the industry does a good job at protecting data at rest and in transit, but does nothing to protect data in use, because data usually has to be decrypted in order to be used or processed by almost all of today's applications, thereby making encryption useless. Since classic encryption cannot be used to protect data in use, the industry has not paid much attention to protecting data in use. Protecting data in this state is a big problem because it is one of the 3 states of data and represents a big gap in the security industry. That's 33%. Hackers always attack the security gaps. Adi Shamir, one of the fathers of the RSA encryption algorithm, says that the mathematics of encryption is okay. Data at rest and data in transit is therefore safe because it is protected by encryption. Data in use is at risk because it's the only place where the data is necessarily decrypted for use by the application and is therefore unprotected by encryption. This unprotected data in use only exists on the endpoint, and that's what Adi Shamir is talking about when he's referring to endpoint security.
So one of the things that cryptography is supposed to let us do is with a very little bit of effort encrypt data so that it takes a huge amount of effort to read it. And there was an email that Bill Gates wrote in 2002 saying that our software should be so fundamentally secure that customers never even worry about it. And I see a great deal of worrying going on. So the mathematical goals that we have with cryptography of getting this great security at a low cost don't seem to be happening. And you look at what the NSA was doing, likewise, they were getting a huge amount of information for relatively, or maybe a modest amount of effort. What should we be doing differently?
In some sense, I think that we should distinguish between the mathematics of cryptography and the application of cryptography. One of the nice things I learned, if I can say this is the silver lining in the Snowden revelation, is that there wasn't any indication in all the hundreds of thousands of documents that the NSA was able to break any of the major crypto systems. For example, they are spending huge amount of money in order to build the quantum computer. So they apparently don't have a fast factoring algorithm, breaking RSA. They have to trapdoor elliptic curve schemes. So if you look at all those documents, there isn't any indication that they managed to break the mathematics. However, it is the applications, the Windows, the Android, the endpoint security, which is suffering.